that we find all of those, but we have a chance to find all of the bugs. If there is a part that does not get executed by our test cases, no way we can find bugs there. So that is the idea that rules systematic test case design. Make sure that with the systematic approach, we cover all of the code so that we can at least have a chance of finding the bugs. So keep that in mind when we talk about how we're going to do systematic test cases. I put the analytical part of the software quality assurance, that is the the right-hand side, the blue part of this picture, into a more detailed picture here. And there you see the dynamic and static testing areas. You see what we usually talk about when we talk about dynamic and static testing. Static testing at the bottom, we talk about reviews, inspections, walkthroughs, informal reviews, technical reviews, audits, all of that. And we talk about static analysis, tools reading through the code, giving us control flow diagrams, doing data flow analysis, checking cyclomatic complexity, and so on. This is not what we will talk about. We will talk about today about black box test case design techniques. So we talk about the dynamic part of testing, and also systematic test case design is in the area of white box testing. But our examples today will all be on the black box side. So talking about systematic test case design, this covers black box and white box techniques. We today will talk about black box test case design techniques. They both have proven to be very good techniques over the years. And there is actually a British standard holding all the various methods that we use to systematically design your test cases. And we will look at some of the test cases that are in this British standard. Here is a subset of the methods, or some of the test design techniques that I understand. Here's a subset of the methods that we're going to use, and these are the ones we will be addressing today. Boundary values, equivalence classes, we do that together, although I will introduce you to boundary values and show you a few aspects of boundary values that might be new to you. We will talk about decision tables and cause-effect graphs, how we can use cause-effect graphs to build decision tables, to simplify decision tables. And as I mentioned earlier, if there is time enough, we do state-based testing, and we will probably look into the approach of pairwise testing to give you an idea what pairwise testing is all about. So let's quickly look or reassess what black box testing is as opposed to white box testing, so you know where we stand. You would have heard of all of that in your foundation level training, but let's just summarize what is black box testing. Black box testing, you can use that as a synonym to functional testing. We want to test functionality. We want to see if things work according to the specification. Again, if we have a multiplier, a function multiplying two numbers, we put 3 and 5 in a multiplier, we look at the result. We look at the 15 coming out as a result, and we compare that to the expected result. So it's input-output driven testing. We produce inputs, and we generate an output, and we compare that output to the expected output. That's basically what we do in black box testing. And because very often the expected output is specified in a document, in a specification document, we sometimes call that specification-based testing. So if you hear that, that is the same thing as black box testing, specification-oriented testing, or functional testing. You can basically use these as synonyms for black box testing. The name black box comes from the idea that we see the test object as a black box that just has 2 input channels in case of a multiplier and 1 output channel. We put 2 things in, 2 numbers in, and we get a result as an output. And how it is derived internally, what is happening internally, we're not interested in that. We only judge its functionality by the input-output behavior. That's the idea behind black box testing. White box testing is a bit different. White box testing is not real testing at all. What we do when we do white box testing is we check if the test cases that we are using for our black box test are good test cases. It basically tests the quality of our test cases, our white box test approach. Because we use the same test cases that we use for black box testing, and what we do in white box testing is we measure the percentage of code that was covered with the test cases. Because we want to cover all of the code. Remember what we said 10 minutes ago? If you do not execute all the code, you have no chance of finding all the bugs. Every piece of code that is not executed, you have no chance of finding a bug in there. Because only if you execute your code with test cases, a failure can show up. And a failure is what we want to produce. That's the information we produce, and we give it to the developers so they can use that information to find the cause of the failure, the defect, and fix the defect. So the structural approach of white box testing simply means that we execute all the test cases that we have generated with our black box test case design methods, and then we measure the code coverage. We look at what percentage of the program was executed, and that is the result of our white box test. The result of the white box test is a coverage percentage, and we can measure different coverages. We can measure statement coverage, have we covered all the statements at least once. We can measure decision coverage, have we gone through all possible decision output, through all possible paths, have we examined all possible conditions. There are multiple coverages that we can measure. That will not be part of today's topic, white box testing. I just explain it to make the distinction clear between the black box testing and the white box testing. There is one area, though, that you can use the white box test approach to actually generate test cases. And that is, if you have found out with a white box test approach that you have not achieved 100% coverage, you can examine the code and see why did we not achieve 100% coverage. You might not have achieved 100% coverage because some area of your code was not executed. So I just draw a simple control flow graph here. So that is like a simplified flow chart through your program, a control flow graph, which has a decision here, might have a second decision here. Maybe there's a little loop in here. So there's another decision here. A decision is a node with 2 outputs. So we might have executed test cases, and all of our test cases moved along this path here, or maybe once around the loop, or maybe 5 times around the loop and then out. None of our test cases moved through this area. So this instruction never got executed. That is something we can find out with the white box test approach. Now, how can we use that for test case design? Well, if we find out that all of our test cases move through this area, none of them move through this area, let's look at this decision here. And let's find out what sort of input data would we need to move into this branch. And that input data is an additional test case that we're using. So in that case, you use the white box test approach to actually generate new test cases. But the most work, the most benefit you get from your white box testing is not test case design. It is just verifying the quality of your black box test cases, of the test cases you have derived using systematic test case design techniques. The third pillar in that group is the experience-based test case design. So that is the non-systematic method. Exploratory testing is part of that. You've heard of that. Error guessing, fault tests. All the testing where you use your own experience and your own knowledge about the project, about the functionality, and about the process, how the software was generated. So you would even know, you would even use things like information about developers. Maybe you know the person that developed the code. And because you know the person that developed the code, and you know that is a very experienced programmer, you do less testing in this area. And there's another area where new people that came directly from university, little experience, where they did the coding, and you would do a bit more testing there, because you assume they make more mistakes than the experienced programmers. So knowledge about the programmers can help you directing your test efforts to the areas that are most probable having bugs, because unexperienced people work there, or because maybe you know there was time pressure in the project when that part was coded. The other part got coded initially at the beginning of the project, no time pressure, but this part of the code was done towards the end of the project. We had a lot of time pressure. So we would assume as experienced testers, if developers work under time pressure, they make more mistakes. So we would do more testing in this area where we had time pressure, less testing in the area where experienced people worked and where we had enough time for coding. So that's the idea behind experience-based test case design. You use the knowledge that you have about the product that you're generating. Again, that will not be part of today's session, just to distinguish between black box, white box, experience-based test case design techniques. So this is what we do. This is the scope of our workshop for today. Equivalence classes, boundary values, decision tables, state transition testing, maybe some pairwise. Other techniques that are available that are systematic test case design techniques, I'm not going to cover. There are some more that are put down here. There are many more other techniques that we are not looking at. Before we go into systematic test case design, let's look generally at designing test cases. Now, keep in mind or make it aware to yourself, something you probably know. Building test cases is not a difficult thing. If I ask you to test a multiplier with two input values, even if it's just an integer multiplier, function that can multiply two integer numbers, and I asked you to generate test cases for that, would you have problems generating 1 million test cases for that? I don't think so. First test case, 1 times 1. Second test is 1 times 2, 1 times 3, 1 times 4, up to 1 times a million. That's a million test cases. That's easy to generate. If you need 2 million, you go 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, up to a million. You have 2 million test cases. So you easily can build a million of a million test cases, which is a trillion test cases. And if you go beyond 1 million for each one of the numbers, you can build even more test cases. So building test cases, building a lot of test cases is not a problem. That is not what systematic test case design is about, but building test cases. Systematic test case design is about reducing the number of test cases. It is about reducing the number of test cases, but still have a high probability of finding errors. So out of the vast amount of possible test cases, we want to pick a subset. And we want to pick this subset that has the highest probability of finding errors. That is the secret of systematic test case design. Because testing a multiplier with, say, 20 test cases and finding the same bugs that we would find with 10 million test cases, well, that's of course the better alternative, because 20 test cases we can easily execute. 20 million test cases we cannot execute. But if we find out of the 20 million, these 20 test cases that have the highest probability of finding errors, then that is a good approach. And that is what we're aiming at. That is the goal of systematic test case design, to reduce the number of test cases, but to keep the test cases that have a high probability of finding errors. So, what sort of approach could we go for? To go for systematic test case design, well, because it is a black box technique, which is specification-based technique, specification-based testing, specification-oriented testing, that was a synonym for black box testing. That is what we want to do. We want to analyze the specification and extract from the specification all the test conditions. Test conditions are the backbones of our test cases. A test condition is a feature that we're trying to prove with testing. We're trying to prove that this feature is actually part of our program. That is the test conditions. We have to find these by reading through requirements usually. That is a major way of coming up with the test conditions. And we do another thing while we read through the requirements. We not only identify the test conditions, we also review the requirements, and we can find out if the requirements are all testable requirements. Sometimes you have requirements written in a document that are non-testable. I'm not sure what sort of requirements you're working with, but I have had a lot of requirement documents that were holding statements from which I said, well, that's really difficult to test this. Have you come across non-testable requirements in documents? Any example? What sort of example were there in the document?
Probably that something like preparations. You might need to prepare hardware-wise, not necessarily software.
Okay, if you have descriptions on hardware functionality that are difficult to mimic with software functions, so that would be difficult to test. That would be an untestable requirement, and if that is in a software specification, then that is an indication that it should not be there. It should be maybe in a hardware description or in the description of our test environment, of the production environment, it should not be in the software description. Any other examples? I'm thinking of examples where things were formulated in such a vague way that it is difficult to test. Have you ever had statements like the software shall be fast? software shall be easy to use. That, you very often have that. The software shall be easy to use. Now, I think that is an example for a requirement that is very difficult to test. How can you prove with testing that the software is easy to use? Easy depends very much on the person that is using the software. Or the screen should appear fast. If you switch to the next screen should appear fast or fast enough. Sometimes I've written statements about the specifications. Now, fast enough is also part of the specification that is very difficult to test. What is fast enough? 500 milliseconds? Or is 3 seconds fast enough for a page to appear? We don't know. It depends on the product. It depends on the people that are using it. So when we derive test cases from specification, when we read through specification in order to find out the test conditions, the features that we want to prove, then we come across these vague statements. And so that's a side benefit from systematic test case design, that you review the quality of your specifications. And if we have derived good test cases from specification analysis, we know that we have a good specification, that we all have testable statements in the specification.